So we've kind of done all the requisite work that sets us up to answer this final question, which is find the points where the normal line intersects the graph of 3x squared. So I had y'all kind of working on the problem, and I was drawing the picture over there, but let's just kind of revisit it. We had the graph of 3x squared, which I kind of drew over here in blue. It should have y-axis symmetry, but mine's okay. And then on part A, we found the equation of the tangent line at x equals -2, and the point ended up being -212. So that was the red line there. That's the tangent line. The slope was pretty steep in the negative direction, -12. And then we wrote the equation of the normal line at the same point, and of course the normal slope is the opposite reciprocal of the tangent line, so that would be positive 1/12. And I drew that in green, so you can see that it's relatively flat compared to the red one, which is relatively steep. All right, so now the last part here is find the points where the normal line intersects the graph of 3x squared. So the normal line is in green, and we know one of the points of intersection, of course, is what? It's got to be the point of tangency, right, which is also the point of normalcy, which is -2, 12. The only thing that we don't know is this other point over here. I'm going to call it x, y. Or you could even call it x what? F of x, which is 3x squared. Yeah, that eliminates the variable. So let's see. How are we going to do that? I know that it's going to probably be an x value that is what in relation to +2? Bigger or smaller? Bigger, because it's higher on the graph. By the symmetry, it's going to be something greater than 2 and something greater than 12. So you just want to write down 3, 14? Or is there a way to find it? Of course there's a way to find it. Yeah, because what do you know about the solution graphically to equations? It's where the two, of course, intersect. So what would we do algebraically to find that? Set their y values equal to each other. Very good. So I want to know essentially where the normal line equation intersects 3x squared. So I got to take my normal line equation, which is from above, 12 plus 112 times x plus 2. I got to set it equal to 3x squared. Right? You're trying to solve an equation. It's where the two intersect and vice versa. So that's how we got to this. Now we just have to solve. Okay, sweet. Any ideas what you want to do first to solve for x? Guess and check? Distribute? So you would embrace the fraction and work with it, or would you clear it out first? Okay. Yeah, it's totally your option. I think most people would probably eschew the fractions rather than embrace them. So if you do that and multiply both sides of the equation by the LCM, and now if you distribute carefully, you get a 144 plus the 112 times 12 divides out to give you 1, and then when you distribute the 1, you just get plus x plus 2. So you don't distribute the 12 into the x plus 2 and divide it out with the 112. Those are two factors in one term. And over here you get 12 times 3 is 36x squared. Good. So absolutely. Now it's looking pretty user-friendly. We can move everything over to one side. So I'll move everything to the right-hand side. So we have 0 equals 36 x squared. That'll be a minus x. And when I combine them on the left, it's 146. So coming across, it becomes minus 146. At what grade level did y'all just start sliding terms across the equal sign and changing the signs rather than subtracting them or adding them to get rid of them? Do y'all remember when? Do you still actually show the subtracting? Oh, okay. I'm just curious because my daughter's in 8th grade and I'm trying to just tell her, no, when you have a term, just slide it across and change the signs. Like, you know, she doesn't want to do that. And I understand why, because you have to understand why it works. But at some point, you move. And I didn't know, but some of y'all still do the okay, well, that's great. Hey, that's fine. That's fine. So now the fun part. When you have something equal to 0, your goal is to what it? Solve it by factoring. Now, the first rule of factoring is to look for a common factor, the greatest common factor, and other than 1 or -1. The leading coefficient is already positive, so I wouldn't factor out a -1. There's really nothing in common, right? So look at this. This is going to be a fun one. We're looking for factors of 36 and 146 that add to give us negative 1. 2?
Well, it's going to be big numbers. So
right. Or we can use the quadratic formula.
What's 12 times 13? What about 70 years?
Yeah. Hey, this is not a difficult problem at all. Why, J. Cables? Absolutely. Don't we already know a root of this equation? That's a quadratic, so it says there's 2 possible values of x. Never lose sight of what it is we're doing. We already have one of the x values, don't we? We know that x equals negative 2 is a solution to that quadratic equation. And remember the factor theorem, since negative 2 is a root or a solution, what's the corresponding factor? X plus 2. And now you can force the other factor. I have an x, and I need to get a 36x squared, so that other factor's got to be what? 36x, right? And to get from a 2 to a negative 146, I need to multiply by negative 73. Now, all you got to do is check to make sure it works. On the inside, you're going to get a positive 72, and on the outside, you get a negative 73. That adds up to give you negative 1. Pretty impressive. So that was kind of important to realize that you already had one of the solutions. And so now, of course, you set them each equal to 0, which you can do in your head, and say, so x equals negative 2, which we knew about, or x equals this fantastic number that if I would have been trying to find by guess and check, I probably would have eventually got to it like in 10 years or so. Okay? And that's the power of the algebra. Now, we've got to make sure we answered the question. Did it just want the x value? Do we now need to do something else with that? Find the points where the normal line intersects. Okay, so I need to find the actual coordinates. Yeah, so the points are negative 2, comma 12. We already found that one. And 73, 36, comma 3, parentheses, 73, 36, squared. How do y'all like that for an answer? I like it. You wouldn't be expected to do anything else with that without a calculator, but that's just 3x squared. Beautiful. Love that question. One of my favorites. Free response style stuff. On a free response, yeah, I guess it would kind of look very similar to that. Yes? Yes, the notes are online and the videos are also recorded. This video was missing, so that's why I'm recording it today for some reason. But yeah, they're up there, and they should match up. Okay, so remember we learned the power rule, and I think we've already seen some examples where we had to first rewrite our function or the expression before we use the power rule, because remember it has to be in the form of a times x to the nth power. And n must be a real number, okay? Now, x cannot be in the denominator. You can't write it as 1 over a x to the n, okay? It has to be in the numerator. So if that were the case, you'd have to write that as 1 over a x to the negative n. It's got to be a times power, x raised to some power. So up above on the previous examples, we did the noun format where I had y equals, and you had to find dy dx. We had f equals, and you had to find f prime. This is going to be the verb format now instead of the noun format. So the instructions are going to be a lot more concise. It's probably just going to say evaluate. All right? So notice we don't have an equation now. We just have an expression with a verb in front of it, right? Which is the instruction itself. This says take the derivative with respect to x of this expression. Okay, well, do you want to use the limit definition, Peter? Say no way. Say, are you kidding? Yes, I'm kidding. Very good. It's National Talk Like a Pirate Day. All right, so we need to rewrite it so we can use the power rule. I got to bring the x to the top. Now, the only thing is if it's in the verb format, you need to bring the instructions down as you're rewriting. So we got a 5/2, and we can kick x to the top, which means we can kick it off to the side. And what's the new exponent? Good. Negative square root of 2. And now we're ready to go. So remember the power rule? How do we differentiate? Galileo couldn't do it, remember? Two basic operations in order. Multiply, subtract. Very good. Now when you differentiate, the d dx goes away. And I will show you why. Okay? The 5/2 is going to go along for the ride. It's a constant. And then you're going to have negative square root of 2 x to the what? Negative square root of 2 minus 1. And what we do then is we multiply by the derivative of that variable x, in this case with respect to x. That's what's really happening behind the scenes. We look for the rate of change of x with respect to itself. Well, what is dx dx? If you had to simplify that, your intuition would tell you it divides out. And it does. It's 1. Okay? So you're not going to have to do that step every time. In fact, here's what you're just going to do. You're going to take the derivative and the d dx goes away. You're just going to say it's 5 negative, or sorry, you got to be careful there. How about negative 5 square root of 2 all over 2 x to the negative square root of 2 minus 1. You can go straight to there. And then if you want to put it back into the radical format that it started with, that would end up being negative 5 square root of 2 all over 2. And then the x jumps to the bottom. And what becomes the exponent in the bottom? Positive square root of 2 plus 1. Good. You change the entire sign of the exponent, which means you kind of distribute through a negative 1. Excellent. So either one of those could be, final answers depending on what we're going to do. If we wanted to evaluate it or use it, the bottom one's probably better. If we needed to go on and take another derivative, as we'll be doing later, then the first one is still in the power rule format. Okay? The minus one? Okay, so when I brought the x to the top, notice how it's x to the positive square root of 2 in the bottom? So when you slide it to the top, you have to change the sign. So that's where I get the x to the negative square root of 2. And then being in the top with the 5 is the same as kicking it off to the side and putting it over 1. So now I have a times x to the n. So I skip this step right here with the asterisk. I can multiply. So what's 5 times negative square root of 2? Negative 5 square root of 2. When I wrote it down at first, I put 5 and then negative square root of 2. But, of course, without parentheses, that looks a whole lot like subtraction. So you got to be careful. So I just pulled the negative in front, put the square root of 2 behind the 5, and then I subtracted 1. Negative square root of 2 minus 1. That's what we do. We multiply and subtract. So it's always this times this to get your new coefficient, and you always subtract 1 to get your new exponent. Okay? And then we just brought it to the bottom. All right, let's look at this one here. Another thing that I say quite a bit is simplify early and often. Okay? It's a lot of times easier to simplify in the front end of a problem than on the back end. So if you look at this, of course, it has powers of x in it, but it's not quite ready to go in the power rule format. So what are some of the things we could do to make it ready? Yeah, very good. Get rid of the parentheses. 2x quantity cubed is 2 cubed x cubed, which is 8x cubed. It's not just 2x cubed. So that looks better already. And then we could do what? Yeah, the 4/8 becomes a half. And in the same line, if you want, then you could bring the x to the top, which means you can kick it off to the side and becomes minus 3. So we like to have it written, remember, as a coefficient times the power of x. So rather than have the x on the top, we'll call it 1/2 and put the x off to the side. Now it's going to make the derivative a lot easier. And again, notice the instructions on what we're doing is still in front, yeah? But now we're ready to take the derivative, so this is where we can drop the verb, d dx, and we multiply and subtract. So 1/2 times 3 is, negative 3 is, negative 3/2. Good. So there's your new coefficient. And your new exponent is negative 4. Yep, negative 3/2 x to the negative 4th. Or negative 3 all over 2x to the 4th. Either one of those. Simplify when? Late and never? Early and often. Great, 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 great. All right, letter C. You do C. It's the derivative with respect to t. What the? Hey, this is why Leibniz notation is kind of nice. You have the independent variable right there, so it tells you what variable you're working with. And you'll see later on that we might have more than one variable in here. So in multivariable calculus especially, it's important to know which one you're talking about changing. And you would hold everything else constant. But in this case, we're just dealing with one variable. rewrite it, differentiate it, and then put it back into original radical form with no negative exponents if it applies. And while that's going on, don't forget this Thursday morning is a pep rally from 7 to 9. Like the first 100 people there get a donut and a shirt. There's a shirt and a raffle ticket. Sure, absolutely. Oh, did she? Oh, true. So let's just, we can meet like for 6 a.m. breakfast and get it ourselves. And that's it. Yeah, we'll talk about that tomorrow after school. That'd be cool. Like, pull an all-nighter, right? You got to combine your t's before you take the derivative. You've got to write it as a single number times a single variable raised to a single power. Single number times a single variable raised to a single power. When we started pre-cal at the beginning of the year this year, we worked with exponents quite a bit, simplifying exponential expressions. And it was because of problems like this. Well, let's see. We got 7/3. That's just a coefficient, so we can pull it off to the side. And we have a t to the first over a t to the 1/2, right? And to combine those, you just use the rules of exponents, right? When you're dividing and the bases are the same, what do you do with the exponents? Subtract. So what is 1 minus a half? 1/2, okay? So that becomes t to the 1/2. In other words, that simplifies to 7 square root of t over t. You can rationalize it as well. Multiply by square root of t over t. You get the same thing. But 7/3 t to the 1/2 is your simplified expression before you differentiate. Number times variable to the power. So now we're ready to differentiate. 7/3 times a half is what? 7/6. You just multiply straight across. T to the 1/2 minus 1 is negative 1/2. And again, notice the d dt is gone. In fact, it's a banned substance. So now if we clean that up, it's 7/6. See, the negative brings it back down. The 1/2 puts it back under a radical. I would practice every time because, again, we're going to be either using it, which means the bottom one is going to be a lot easier to evaluate, and the top one would be ready to go then for another round of differentiation fun. Yes? Why is it not what? Oh, that's for inner. Go ahead. Multiply and subtract. 1/2 minus 1. Oh, no. See, here's what I did. Y'all can have a good lunch. I'm going to clarify how I got this right here. If you want to do that, you could do this. You have a t in the top to the first. That's a t to the 1/2 in the bottom. But when you bring it to the top, it becomes t to the negative 1/2. And then I combined these exponents before I took the derivative. What's 1 plus a negative 1/2 or 1 minus a half? Positive 1/2. In other words, I simplified this expression. Oh, yeah. No, when I said 1 minus a half, I was just assuming that we would leave it like this. Just leave it as the square root of t in the bottom, which is t to the 1/2. And then the rules of exponents say when you're dividing and the bases are the same, you subtract. So that would be 7/3 t to the 1 minus a half power. I think we're getting confused on simplifying from the original expression versus the rule for derivatives where we multiply and then subtract one. Okay. Good.